So today we start our chapter on quadrilaterals, and we're going to discuss polygons today. What is a polygon? What does the word or prefix poly mean? Poly means many, so a polygon, by definition, is a many-sided closed figure. So here are some examples of different polygons. They can look very different from each other. As long as there's many sides and it's closed, then you have a polygon. We can name our polygons based on the number of sides that it has. You need to know these names. They will probably show up on a quiz and definitely on a test in definitions or in instructions. If I say to draw a pentagon, then you need to know what penta means. So let's go through these and name these polygons based on the number of sides they have. Three-sided polygon you should know is a triangle. Tri meaning three, like tricycle. 4 is quadrilateral, which we will go into more detail in this chapter. 5 is the pentagon. Okay, there is a government building called a pentagon. If you look up an aerial view of it, you will see that it is a 5-sided building. 6 is hexagon. 7, heptagon. Those two are real easy to get confused. They sound very similar. Hexagon is 6. Remember the X's go together. Heptagon is 7. 8, like an octopus, has 8 legs. An octagon has 8 sides. 9-sided object is called a nonagon. 10 is a decagon. 12 is a dodecagon. And then from that point on, we do have names for the other numbers of sides, but just for simplicity's sake, we can just use the number of sides as part of the name. So for example, if we had, say, 36 sides, we would just say a 36gon. Okay, rather than memorizing an indefinite number of names. Once we go above 12, we'll just use the number. Okay, but I do expect you to have all of these memorized. Within the group of polygons, we have special ones called regular polygons. If you'll remember when we talked about triangles, we said that there are such things as equilateral triangles in which all sides were congruent. Or you can have an equilateral polygon as well, where all sides are congruent. We also had equiangular triangles in which all the angles were congruent. Well, you can have equiangular polygons because triangles are polygons. Remember, they're 3-sided polygons. If you have a polygon that is both equilateral and equiangular, then we say it is a regular polygon. It has to have both. It has to be equilateral and equiangular. And you will be shown that in the markings, like so. Notice that this quadrilateral, 4 sides, all 4 sides are congruent, therefore it is equilateral, but are all 4 angles? No, they are not. Okay, so let's go through this and see which ones are regular and which ones are not. Okay, so that's a quadrilateral. We know that because there's 4 sides. We said yes, it's equilateral because all 4 sides are marked as congruent. Are all 4 angles marked as congruent? No, so it's not equiangular. So can it be regular? No. It has to have yeses in both of these areas. Now let's go on to this next figure. To name it, we need to know the number of sides. So we got to go around and just start counting. 1, 2, 3, 4, 5, 6, 7, 8. What was the name of an 8-sided figure? Remember, there's an ocean creature that has 8 legs. We call it an octagon. Is this octagon equilateral? Are all of the 8 sides congruent to each other? Yes, they are. So we're going to put a yes in that box. Are all of the angles marked congruent? There are no markings here, so we can't make any assumptions. Okay, even if we did go by looks, it looks like all of these obtuse angles here are the same, but then this appears to be a right angle, this appears to be a right angle, and this is way more obtuse than these. So we're going to say no there because we have nothing to tell us that they are the same. So is this a regular polygon? The answer would be no. Remember, they have to be both equilateral and equiangular. So let's look at our last figure here. Again, we need to count the sides. 1, 2, 3, 4, 5. What do we call a 5-sided polygon? Pentagon. Is it equilateral? I see 5 congruency marks on those sides, so yes it is. Is it equiangular? I see the same congruency marks on all 5 angles, so yes it is. So is it regular? Yes it is. Another way to identify polygons is we use the term concave and convex. Okay, concave means it caves in, like so. Notice that the side goes into the interior of that polygon. Okay, if it caves in, kind of like a Pac-Man, then it's concave. Otherwise, it's convex. So what would this one be? Do any of the vertices go into the interior of this polygon? No, so this one's going to be convex. Okay, so know the difference between concave and convex. So not only do you need to be able to qualify them as either, based on their name, also are they regular or not, are they convex or concave? So different ways to classify and name polygons. Within polygons, we can draw what are called diagonals. A diagonal is a segment that connects two non-consecutive, there's that word again. What does consecutive mean? It means one right after the other, so side by side. So we're connecting 2 vertices that are not side by side in a polygon. So a diagonal would look like this. We start at one vertex and we're going to draw a line to another vertex that is not right next to it. So we can't draw it on this one. We can't draw it on this one if we're going to start here. How many diagonals can we draw in this figure? This is a pentagon. 1, 2, 3, 4, 5. We're able to draw 2 diagonals. Here we have a 1, 2, 3, 4, 5, 6, 7, 8. So this would be an octagon. How many diagonals can we draw from this vertex in this octagon? We can't draw it to here, and we can't draw it to here because those are right next to it. We need to draw it to the other 5. So we can draw 5 diagonals there. So be able to chop up your polygon with these diagonals. And this is important when we're trying to decide what the angle measures or the sum of the interior angles are going to be, because notice By drawing these diagonals, we're chopping our polygon up into many triangles. Okay, so interior angles of a polygon. Interior means inside. So we're talking about these angles. These are our interior angles. And these are regular polygons. It appears. I can chop them up again into several triangles just by drawing diagonals from one vertex. I just pick one vertex and I draw all the diagonals I possibly can from that vertex. And that chops my figure up into triangles. So if I want to know the sum, what does sum mean? What am I doing mathematically? We're adding. So if I want to know what the sum of all of these interior angles would add up to be, I can think of it this way. Well, how many degrees are in a triangle? I hope you remembered 180. So for each one of these triangles, I have 180 degrees. How many triangles do I have? 4. So the sum of those angles inside that hexagon is going to be 4 times 180, which is 720. Okay, let's try it over here on our pentagon. If I pick a vertex down here and I draw all of the diagonals, how many triangles am I going to get? Okay, that's all I can draw. So I get 3 triangles. Each one's 180. So what's the total degrees in that pentagon? 3 times 180, which is 540. Okay, pretty simple. So to sum it up, we actually have a theorem. It says the sum of the measures of the interior angles of a convex n-gon, any kind of polygon, is n, which is your number of sides. N is the number of sides. So if you subtract 2, it's going to give you the number of triangles, times 180. Okay, so let's do this again. If I had an octagon, okay, you could draw it out if you wanted to. 1, 2, 3, 4, 5, 6, 7, 8. And you can draw all of your diagonals and then count your triangles. 1, 2, 3, 4, 5, 6. Okay, so I had 6 triangles times 180. Or I can use my formula where I don't have to draw it out. If I don't have a picture, I don't have to take the time to draw it out if I know this formula. According to this formula, it's always going to be the number of sides minus 2. That's how many triangles I'm going to get. So if I have 8 sides here and I subtract 2 from it, that gives me 6 triangles. It's always going to be minus 2. Okay, so you can draw it or you can use the formula. It works either way. What if I wanted to know how much just one of those angles measured? I want to know each interior angle. Well, if I know the total and I know that I have 8 angles, I'm just going to divide by the number of angles. Okay, so remember, n is the number of angles or the number of sides. They are going to be the same. You're going to have the same number of sides as you do angles. So if I want to know the total, I use this top formula. Or again, I just count my triangles and multiply by 180. If I want to know what each angle is going to be, then I then divide by the number of angles. Now remember, this only works for a regular polygon where all the angles are the same. So let's do an example here. A mall is designed so that 5 walkways meet a food court that is in the shape of a regular pentagon. So if you didn't have a picture, you would need to know what a pentagon looked like. Find the sum. Okay, so here I just want the sum of the measures of the interior angles of that pentagon. So I can either use the formula or I can sit here and split this up into different triangles. I'm going to have 3 triangles, so I should have 3 times 180, right? Or I can use the formula, where the formula is 180 times the number of sides, which is 5, minus 2. So either way, I get 3 times 180. Which is 540. Okay, so the sum is 540. Here's another one. A decorative window is designed to have the shape of a regular octagon. Find the sum of the measures of the interior angle. So again, let me use a darker color here. I could either count the number of triangles or I can use my formula. I have 8 sides. I'm going to subtract 2 from that, and then I'm going to multiply that by my 180. So 6 times 180. Let's check that and make sure that's right. So here's 1 triangle, 2, 3, 4, 5, and then this one is 6. So yes, 6 times 180 is answer choice C, 1080. What if I wanted to know what just one of these measures was? I would take this total and I would divide it by the number of angles that I have. And it's an octagon, so I have 8. Okay, and that would give me my one angle. Okay, here's another type of problem you might encounter. We're trying to find this missing angle here. Now, this is not a regular polygon. How do we know it's not regular? Because the angles are not the same. But the sum is still going to be the same as no matter whether it's regular or not. I still have the same number of angles. How many do I have? I have 1, 2, 3, 4, 5, 6, 7. 7 angles. So I'm going to take that 7, subtract 2 from it. That gives me 5 triangles. Each triangle is 180. So I have a total of 900 degrees. Now, how am I going to find this missing angle if I know all of these add up to 900? Well, I'm just going to add them all up and set them equal to 900. Okay, so each one of these is an angle in that polygon. Add up the ones I know, I get 760, then subtract. My missing angle is 140. The measure of an interior angle of a regular polygon meaning they're all the same, is 130. Find the number of sides in that polygon. Okay, so here's another twist using the same concepts. This time I know what one angle is. I'm trying to find out how many there are. Remember, n means number of angles. So anytime I'm dealing just with one single angle, I'm going to use my formula for the sum of my interior angles and divide it by however many angles I have. Okay, it's the same formula, it's just that I know my angle this time. I'm looking to see how many there are. Okay, a lot of people forget how to deal with variables on the bottom. Remember, if something's on the bottom and you want to get rid of it, you need to put that same thing on the top. So I need to multiply what I do to one side, I need to do to the other side. This way my n's cancel. So I end up with 135n, and then the top here stays the same. Now what am I going to do? I have a set of parentheses with something outside my parentheses. I have to distribute Okay, now it should look familiar to you. Okay, we moved our n over, we subtracted 180. Oops, 180, pen didn't want to work. 135 minus 180 is negative 45. Now divide by that negative 45 and I get 8. So how many sides did this polygon have? It had 8. What would we name that polygon? An octagon. The measure of an interior angle of a regular polygon is 144. Find the number of sides in the polygon. So again, I know what one angle is. I don't know how many angles there are. But I know that if I take the sum and divide it by however many angles there are, I'm going to get that one angle. Okay, one angle is the sum divided by the number of angles. That's why we're setting it up this way. I'm going to multiply both sides by n to get that one off the bottom. So 144n equals n minus 2 times 180. I need to distribute here. When I distribute, I get 180n minus 360. Subtract the 180n so that I get my n's on the same side, and I get negative 36n equals negative 360. Divide by that negative 36 and n equals 10. So our correct answer is D. Interior of angles of a quadrilateral theorem. Okay, quadrilateral, 4 sides. Doesn't matter what those 4 sides' lengths are, the sum of the interior angles of a quadrilateral will always be 360. A square, a rectangle, a trapezoid, anything with 4 sides is going to have an interior sum of 360 degrees. Okay, so you just add up all 4 angles and they will always equal 360 degrees. This still goes along with our n minus 2 times 180. Okay, n is our number of sides. If we have 4 sides, then that's 2 times 180, which is 360. So this isn't anything new. This is just one that you're going to use more than any other. So if you can just memorize that a 4-sided object has a sum of 360, it's going to save you some time. Okay, so here's the sample problem. Find x. Well, if I know that all 4 of these add up to 360, then that's exactly what I'm going to do in my equation. I'm going to add them all 4 up and make them equal to 360. Combine like terms here and x's here. Move the 150 over, divide by 3, and you get x is 70. Now, I could ask you to tell me all 4 angles, in which case this would be 70, this would be 140, 65, 85. Okay, here's another one very similar. Only this time it says to find the measure of each interior angle. So what are we going to do here? What is the relationship of all four of these angles in a quadrilateral? Again, we know that the sum is going to be 360. Okay, so we're going to add it all up and make them equal to 360. So we have 5x, x plus 4, 11x plus 4, 5x, and 11x plus 4. Combine your like terms. 11 plus 11 plus 5 plus 5 is 32. 4 plus 4 is 8. Subtract the 8, divide by 32. Okay, so that gives me x. But remember the question was find each angle. So now we have to go back and plug them back in. Our 5x angles are going to be 5 times 11. Okay, so this comes down here. And then our 11x plus 4, 11 times 11, because again, x was 11. That's where this came from right here. Plus 4 is 125. So we have two angles that are 55, and we have two angles that are 125. You can always check yourself by adding these four up and making sure that they equal 360. Okay, same idea here. I'm not going to take the time to work this out, but your equation should be 6x plus 6x plus 10x plus 3x minus 15 equals what? Equals 360. So see if you can do that one. Pause and work it out. The answer is C. Okay, so that deals with interior angles on the inside. Now we have exterior angles, the outside of a polygon. Okay, in order to find our exterior angles, just like we did in a triangle, we're going to extend the sides to create these angles on the outside at each vertex. Notice it makes a circle when we do that. How many degrees are in a circle? I hope you remembered it was 360. So it does not matter how many sides you have. The sum is always going to be 360. This is an easy one to remember. The sum of the exterior angles of any convex polygon is 360. Okay, just remember that it makes a circle, and that'll help you remember that it's 360 degrees. Now, again, if we want to know what each one is, we're just going to divide by the number of sides. Remember, this is number of sides, or you could say number of angles, sides, because they're the same. Okay, so let's do some examples. Find the measures of an exterior angle and an interior angle of a convex regular nonagon. Okay, they didn't draw it for you. You have to know what a nonagon is. A nonagon has 9 sides. So it would look something like this. We're trying to find one of these angles, and then we're going to find this other angle, this interior angle. Okay, well, what do we know about the sum of the exterior angles? We know they're 360. And if it has 9, then I'm going to take that 360 and divide it by 9 to find the measure of one angle. Okay, so my total is 360. I have 9 of them. So I'm chopping up this 360 into 9 equal pieces. Each piece is 40. So I divide by 9. Okay. So the measure of one exterior angle is 40 degrees. Now, how do I find the interior angle? Well, if this is my exterior angle, whoops, let's go back. Let me go back to my picture here. If this is 40, what is this interior angle going to be? Well, notice they make a straight line together. How many degrees are in a straight line? I hope you remembered it was 180. So this has to be 140 so that together they make 180 degrees. So once you know the exterior, you can easily find the interior, and vice versa is true as well. So let's do one more example of that. I know this one's running long, but I want you to understand how to do these calculations. Okay, we have a hexagon. So we need to find the exterior angle of this hexagon. Well, the sum is 360. And if I have 6 sides or 6 angles, then each one's going to be 60 degrees. Okay, now to find the interior, I just make sure that they add up to 180 because they make a straight line. Well, 120 plus 60 makes 180, so my answer would be C. Okay, so again, I know this was a longer lesson than usual, but make sure you can calculate sums of interior, sums of exterior, and individual interior, individual exterior angles, and know how to name polygons.